A&A Physics, it's Mr. Neff. Today, let's start our talk about coupled masses. And before we do, did you hear about the duck that went to the grocery store? He went up to the cash register to pay, and he gave him a $100 bill. And I'll finish that story at the end of the video. Now, when I say coupled masses, I mean two masses, or two or more masses, that are somehow stuck together so that they have to accelerate as one system. Now, they might be stuck together because they're tied together, like this system over here on the upper left. This system on the upper left is a really common one, so common that it has its own name. It's called Atwood's machine. It might be something like this that you might call a modified Atwood's machine, where you have a mass sitting on a tabletop. Maybe there's friction, maybe there isn't, and the string is going over a pulley and it's attached to another one. Maybe you have something like this where the tabletop's slanted. Maybe it's not something that's so physics classish. Maybe it's something where you're just pushing a shopping cart and all those things are together with friction inside of the shopping cart or normal force in the shopping cart, and they're all moving as one piece. Or maybe you're pushing a bunch of boxes. Or maybe you're just some kids on the school bus and you're all moving together and you have the same acceleration as the school bus has. All those are examples of coupled masses. And so we're going to analyze that one of the simpler sets of coupled masses, this Atwood's machine, right here. Now, our friends over at the Physics Classroom have a really cool demo of this, simulation of this. And what they have is they have a system that you can place coupled masses together in a lot of different ways. Well, what I'm going to do is I'm going to attach or set up an Atwood's machine, something like so. And as you can see here, I'm going to take this. I'm going to place the blue one down a little bit, the red one up a little bit, and I'm going to go up here and push start. And when I do, now notice something, please. The blue one is 19.6 newtons. It's 2 kilograms. And the red one is 19.6 newtons. It's 2 kilograms. Now, when I let this go, I want to know what's going to happen. I want you to stop the video, think about what's going to happen. If you have a neighbor there, someone there to check, I want you to check them, and then start the video again. Okay, we're back. So let's run this simulation and see what happens. 1, 2, 3. Simulation's running. It's running. See, it's still running, and nothing is happening. Now, why wouldn't something be happening right here? Well, we don't have any unbalanced force. See, the force of gravity down on the blue one and the force of gravity down on the red one are the same. And so even though this goes around a corner, if you have a force in one direction opposed by an exactly opposite force in the other direction, and so they're canceling each other out. And so we're not getting any acceleration there. Now, it wouldn't be true if I switched to a heavier mass, and so now if I start this, then the heavier mass is going to accelerate down and the lighter mass is going to accelerate up, because now we did not have unbalanced forces. Now we had a bigger force down and we had a smaller force down on this side, and so we don't have balanced forces. I think a second ago I missaid that. We don't have balanced forces, we have unbalanced forces, and so we're going to get acceleration the way we always get with unbalanced forces. A similar idea. So now I have replaced the red hanging mass with a mass that's on a cart on a table. Now, see here, the force of gravity is still going down, and there is a normal force up because there's a table now, but that's not opposing the motion. It's at a right angle to the motion. So when I click start, this has no chance of staying in place. All we're going to have is the force of gravity down on the blue one accelerating the whole system. There we go. You can see that that's happening. So in that last one, which with the two hanging masses, we call that Atwood's machine, we do have a chance of it staying in place, but it might not. If the masses are different, the forces will be different, and we'll have a net force on the system. But here, there wasn't an ability. Now, in real life, maybe there's not wheels on this, and maybe there's friction, and it could just hang. Or maybe it could have friction, and it could just slow down the acceleration. Regardless, you think about the system's net force And so you're going to be able to see the system's acceleration from that. Now, say we had a similar thing where here's an Atwood's machine, two hanging masses from a pulley that we consider as real smooth, real frictionless. And we have 1.5 kilograms on this purplish left block, and we have only 1.2 kilograms on this reddish right block. And I'd like to know what the acceleration of the system will be, and I would also like to know what is the tension in the string between the two. Okay. So now what I'd like to do is I would like to draw a free body diagram for each side. Free body diagram of the purple one, free body diagram of the red one. So I have those already done underneath these boxes. Why don't you try to draw a free body diagram there and stop the video, try to draw that free body diagram, and then come back and we'll see how you did. Okay, we're back. And on this side, since this is heavier, we know that it's going to accelerate down. So I know there must be a net force down. So here it is. I've got a force of gravity that's going down, mg, and I have a force of tension that's going up. This isn't going to just accelerate down as if it was falling. Now on the other side, we're going to have a similar thing, but a little bit different. Now on the other side, it doesn't weigh as much, so the force of gravity isn't as large. Now the tension in the two sides of the string are going to be the same size, because if this pulley is really smooth, really light, really frictionless, then it's impossible to stretch one side of the string more than the other. So that's going to create equal tensions. So you'll see that these two purple tension forces on both boxes are the same size. So see how those two are the same size, but because of the different weights, it shows that the purple box is going to accelerate down and the red box is going to accelerate up. Now, because of that, we're going to actually be able to calculate what the acceleration and the tension in the system is. So now, here's what we're going to do. I'd like you to stop the video and I'd like you to write a F equals ma equation for each box. So F equals ma for the purple one and a separate F equals ma for the red one. The symbols I'm going to use are going to be force of tension. I'm not going to distinguish 1 and 2. And force of tension, they're the same size, so we'll just use the same symbol for them. And we'll call this force of gravity 1, so calling this mass number 1, and force of gravity 2. So in my equation, you're going to see force of tension, force of gravity 1, force of gravity 2, mass, acceleration, that kind of thing. So stop the video, try to make yourself an F equals ma equation. All right, and we're back. Now, see what I did here. The one thing about coupled masses is you have to think about not up and down, left and right. You think about which force is winning the tug of war, and then you call those positive forces, and which force is losing the tug of war. Now, that's a little funny in this case because on object number 1, the force that's winning the tug of war is the one that's down. I'm going to call that one positive. The one that's losing the tug of war, I'm going to call negative, so that was the tension. So positive is the down force and negative is the up force. That's a little strange, but it gets a little stranger because over on the other side, it's the opposite. The thing that's winning the tug of war, and I know that because of the way it accelerates, is this positive force of tension. That side is going to accelerate up. And the thing that's losing the tug of war is this force of gravity too. So I'm going to call that negative. And you'll see that in my equations. So see, sum of the forces equals ma, and for some of the forces, I always put the positive force minus the negative force. And so there it is, force of gravity 1 minus tension equals mass 1a. And then I substituted numbers. Remember, the mass 1 is 1.5. Over on the other side, a little different. I have sum of the forces equals ma, same, but I have force of tension minus force of gravity 2 equals m2a. See, I'm not thinking about up and down, and if I do, I'll get a little confused. What I'm thinking about is I'm thinking about which force is winning and which force is losing. And so in both cases, both sides, the force that was winning is the positive one, and the force that's losing is the negative one. And remember that when we let this go, you're going to see acceleration down on the left and acceleration up on the right. And so that tells you which forces are winning and which forces are losing. Now you can see what I have. I have a little system of equations here. Equation number 1, maybe we call it. Equation number 2, we call it. And we have to solve that. Now, some people are going to substitute. Some people are going to eliminate. Some people are going to use a matrix. Some people are going to use all kinds of different graphing, all kinds of different techniques. I want you to try to solve that system of equations now. Pause the video so that you do that. And I'm going to, when we come back, I'm going to have a solution presented here for you. Now, what I've done is maybe a technique that you wouldn't have done. Maybe you wouldn't have thought to do it this way. And don't think that my way is the way or a better way than yours. It's just a way that I like to do. So what I did is I took the 2 yellow equations and I added the 2 equations together. So see, I took the 14.7 minus force of tension equals 1.58. Here it is there on the top. I did the force of tension minus 11.76 equals 1.28. There it is on the bottom. I'm adding the 2 of them together. It's legitimate because I'm saying, well, I got 2 things that are equal in the first equation, 2 things that are equal in the second equation. So I'm just adding 2 equal things to 2 equal things, and I'll get 2 equal things. Now, the beauty here is the tension is going to add out. See, I have the 14.7 and 11.76. They don't have a variable. They're like terms, so they add up to 2.94. But I also have a negative tension and a positive tension, and it adds up to 0. On the other side, I have 2 like terms with a's, and so I have 2.78. And so when I divide, I end up getting an acceleration of 1.06 meters a second square. Probably the same thing as you got, even if you use a different technique than me. Then, if I also wanted to know the tension, and a lot of problems do ask for the tension, then I could go like so. I could say, I could put the A into either one of the equations. I went into the one on the left, 14.7 minus the tension equals 1.5 times the acceleration, and I solved and I got 16.3. I'll just point one more thing out before we go, and that is this line right here was actually pretty significant. You see what this was? This line was the net force equals the mass times the acceleration of the whole system. See, what we had is we had a system where we had one object and another object, and we had 14.7 and we had 11.76. And so those were at odds with each other. I know in this picture it looks like they're both down, and they are, but one is moving forward with the system and the other one is pushing the system backwards. And so my point is the net force between those two is the 2.94. And we had a 1.5 kilogram mass and a 1.2 kilogram mass. And so the total of the system is 2.7. And so someone may have been able to just say, oh, you know what? In retrospect, we could have just jumped right to this yellow line and we could have gotten the acceleration that way. And that's true. You could have. And that's a quick, easy way to do it. Some people don't follow that part. But if you do, it might be a nice way to know how to do it too. Okay. So I hope you picked up the basics of coupled masses there. And like I said at the beginning, that duck went shopping. And he went to the grocery store and he went up to the register to pay. Gave them a $100 bill and they said, come on, $100 bill, don't you have exact change? And the duck said, nope, I'm sorry, I only carry bills. See you next time.